started. So welcome to this session on algebraic complexity theory. And I'll just tell you what my rough plan is for the next 3 sessions. So in the first lecture, I'll just introduce you to the very basic concepts in algebraic complexity. What are the typical models of computation, connections to Boolean complexity theory, structural results, and so on. In the second lecture, I'll talk a little bit about lower bounds. So tell you how to prove lower bounds in algebraic setting and what they mean for general, Boolean lower bounds and so on. And then finally, I'd like to show you this connection between hardness versus randomness connection in the algebraic setting. Yeah? And then the center of it all is this problem called polynomial identity testing problem. Okay, so I'll talk a little bit about that. So that's kind of my plan. And why I call this a rough plan is because maybe somebody says something interesting and we go a little bit in that direction, and then I don't cover this whole plan. Whereas maybe somebody proves something tomorrow and I present that instead. So we'll just take it a little more fluidly, but roughly speaking, this is what I would like to cover. All right. So just to know my audience, I would like you to, no, not this. Where was it? Yeah. I would like you to go to something called as menti.com. This is also to kind of wake you up from the afternoon slumber. And then you have to type that code up there.
What website? Menti.com.
Menti.com, it's like right there. And then you go to this code, go give this code.
Is it the year we just finished or the year we're about to start?
Yeah, let's not get too technical about this. Like, yeah, loose interpretation of this question. I know, like, all of you are mathematically oriented, so you want like the exact thing. But I would say maybe like you just finished 2 years. I would say 1 or 2, right?
Do you have a less than 0 option?
No, unfortunately. But I know that you are. Okay, other people who are less than 0. I very thoughtfully put this, and I was very happy with myself. But I, of course, forgot. So below, have not started their PhD yet. Okay, so there are a few, of course. Great. Yeah, so that's great. So many of you are just starting out, and then some of you are in your 3rd, 4th, 5th, 6th, etc. And then the next question is, what's your research area? So how many of you are working in things related to complexity is what I want to know, and then how many are very far away from complexity. So just so that I pitch it right, more or less. Proof complexity, TFNP, zero knowledge proofs, crypto, complexity, coding theory, quantum, optimization, and the works, I guess. And this is like word cloud, so complexity is getting bigger, I see. Circuit complexity. Nice, okay. You could also, for those who've not really started working on their project on PhD or something, you can just say the topics you're interested in. This is fine too. Yeah, thanks for the thumbs ups. All right. And then we have one more question, very quick. What would you expect from this course? So what would you like to learn from this mini course that you're taking in algebraic complexity? So, like, don't write an essay, right? Like, just write like 1 or 2 words that would be interesting for you. So this is like expectation management. Maybe you expect, GCP to be presented here, and I'm going to disappoint you. But on the other hand, if you're here for something else, maybe I can accommodate it within my plan. So it helps to know a little bit. Definitions and key ideas, yes, we'll do that. Lower bounds for constant depths, yes, we'll do the proof. Algebraic hardness versus randomness, yes, we'll do that. Why the permanent is so important, yes, we'll talk about that. Some something algebraic. Okay, yes, sure. How to be good at CS? We will not cover that. Okay, I don't know. Yeah, let's see. Then polynomial identity testing, yes, we will do that. And overview, yes, we will do that. Okay, great. So I think the expectations are kind of aligned with what my overall plan is. Cool stuff, yes. Nice open problems, yes. Learn to use algebra, depends. Yeah, okay. Yeah, so we have a little, I would say that our expectations are more or less aligned. Yeah. So if somebody had said GCT, then I would be scared that I'm really going to disappoint you, but oh no, I know you're there. Okay, but, okay, so thanks for this. And actually, I mean, I use this Menti in my course, but here I just expect all of us to speak up. So this was just for fun. Yeah, just ask me questions and let's make it interactive. Yeah. Okay, so we get started now. Algebraic complexity theory is a study of polynomials. You just want to understand how difficult certain polynomials are and why certain polynomials are easy to compute. Yeah. And why would one care about polynomials themselves? I would say it's because they come up very naturally in many other areas of complexity and algorithms. So they come up in many algorithmic problems like computing the perfect matching, for example. There is an underlying polynomial. They come up in mathematics, they come up in linear algebra, they come up in coding theory. You saw this, some of you attended the coding theory session this morning. You must have seen the Reed-Solomon codes, which are basically polynomials, right? So they come up naturally. Another reason to study them is that there are very, very simple things about polynomials we have no idea how to answer. So here is a very simple question for you. First open question. Yeah, this appears also in the book by Avi Victorson. If you've seen that book, if you haven't, please take a look at it. It's a book on complexity theory. And in the chapter about algebraic complexity, this is one of the first problems he mentions. So what's the problem? I want you to give me an explicit polynomial on just one variable. Yeah, that cannot be computed with order log d operations, but has degree d. So, I mean, you can always think of the following polynomial, which is x to the d. That certainly has degree d. Yeah, and if d is a power of 2, yeah? Suppose d is like 2 to the k for some k, then you have a very simple log d size circuit for this, right? You just repeatedly square x. Log d times. Yeah? So it's very easy to answer that there is a polynomial. I mean, this polynomial has size log d formulas, yes?
Do we know if such a polynomial exists and we just don't have an explicit example?
Yeah.
Okay.
That's some random randomization will tell you that such polynomials must exist. We just don't know an explicit one. If d is not a power of 2, even then I claim that you can do something similar, because you can compute all the powers less than d and just put them all together. Like if it was like 37 or something, then compute the power 32 and power 4 and power 1 and then multiply them all together. So you still have a log d size circuit. Yeah? One doesn't know how to come up with an explicit polynomial that requires more size. Yes?
Are the polynomials always integer powers?
Yes. So the powers are always integers. The coefficients can be anything. Okay, great. So just basic curiosity can make you think about polynomials and questions about it. That's kind of the point of the slide. That, of course, there are many compelling reasons, but even something as simple as this, we do not know how to answer this, and this could be something like a puzzle that you get obsessed with, right? So it is interesting to study that. All right. So when we talk about complexity, we better talk about models of computation. And before I introduce the formal models of computation, let me again give you another example. Yeah, this is a very simple polynomial. I like to talk about it every time I talk about complexity, because it's a very simple example to convince you of some of the points. So what's this polynomial? You take a subset from the universe. In fact, you take every subset of the universe, and for every subset, you multiply the variables out, which are indexed by the set. Add all of them together, that's your polynomial. This is often known as the monomial representation for polynomials, sum of monomials. Yeah, this is, every polynomial has this representation, always. Right? Now, you can do the math in the head, but this is also the same polynomial. Yeah? Except the first one has 2 to the order, like 2 to the n operations, order of 2 to the n operations, and this one has only order n operations. Yeah? So the operations that I'm counting here are plus and multiply. Okay, those are the only things I'm going to charge you for. Yeah, and over here there are exponentially many of them, here there are linear of them. So, you know, you're paying far less in this representation than the one above. Okay. Another subtle point, but maybe important, it will come up later, is that the first representation is like the sum of products representation, the monomial representation. The second is kind of like product of sums representation. But if we just want to assume that the top gate is always a plus representation, which we will do for now, from now on, then it's like a plus product plus representation. Yeah, we call this sigma pi sigma sometimes. Sigma stands for plus, pi stands for product. Yeah. Anybody who has used LaTeX knows this, obviously. Yeah. So this is a sigma pi sigma representation, and that's way cheaper in this case. So it kind of immediately raises a bunch of questions, right? Are these representations always more succinct than this representation? What's the deal? And yeah, I mean, we are only going to talk about these operations. How expensive? Given a polynomial, can you tell me what's the best upper bound for it? You know, this kind of questions. So now we can just introduce the model of computation. And this is something that is very natural. Yeah? The model of computation is quite simple. Just take a bunch of products and plus gates, link them together as you like, and each gate computes, it's called a gate. Each operator is called a gate in the circuit, and then there's like a designated output gate that computes the whole polynomial. Yeah? Questions about the model? It's quite straightforward, I guess. And the number of operations is whatever are the number of operators used. In this case, it's 8, I guess. And then the depth is the number of these layers of cascading that you have. So plus, multiply, plus, it's 3, so the depth is 3. As I said, this could also be called a sigma pi sigma circuit. Yes, question?
You're doing a fan out.
Yeah, good question, right? So you can assume that here the fan out is unbounded, and even fan in is unbounded. It's bounded by the overall size, I guess, but that's it. Yeah. So you could have like S square, whatever, S, quite a few edges, if, yeah. But all the edges go between 2 consecutive layers, that we assume. Other questions?
Where would the coefficients go?
Good question. So coefficients are also at these points. I just didn't draw them, but like you could have other stuff here. The inputs are either variables or constants. And you are allowed to use them as you like. As many times as you want. I'm not going to charge you for that. Yeah, but I mean, it makes sense if you have like x1 being used 3 times, just like put a large fan out. It doesn't make sense to copy it again and again. A formula is basically a circuit, except for this fan out question. Here you only have one fan out 1. So it's like the underlying DAG you have is a tree. So then it's a formula. So circuits and formulas. All good?
Do
Question?
you have a limit on the number of constants you can use at the lowest level? Like
Number of constants you can use?
I can use 2 ones instead of 2 and 4, for example, right?
Yeah, but I think if you can do something very quickly, like small computations, I won't charge you for that. It's like order 1 for me.
Okay.
Yeah, but if you want to use pi and e, then there are like 2 different constants. It's not clear how one can compute one from the other.
You said fan out. What does that mean?
Fan in and fan out. I think there was a question about the fan out. It's like the number of wires out of a gate is fan out, correspondingly the number of edges into a gate is fan in.
Okay.
So for a tree, you can imagine that you can have a large fan in, but for it to be a tree, every node could be used only once. So fan out is only one.
So this one's not a
This is not a formula, yeah. This is a circuit. Exactly. Yeah?
If we're putting constants in the base layer, yeah. Like what if I want my constant in the third layer?
Yeah. You could like put a constant here, I won't really object, but you could also, for example, like put a constant here and like just add some dummy nodes and make it travel all the way.
And the claim is that the dummy nodes won't blow things up too much?
Yeah.
Right.
One has to be a bit careful, but yeah, within polynomial, yeah.
I've seen some formalizations where the plus gates to like an affine transformation like ax plus b.
Yeah, yeah. So the question was, there are some formulations where these linear gates are not just variables feeding in and constants, but just directly this whole thing is one big summation gate. You know, like this, it's allowed to do a huge summation on in itself. They are equivalent if this summation is like polycized, but you have to be a bit careful. So we'll assume this for our purposes. Wherever I allow for linear forms, I'll let you know. Yeah? Can be simulated by this, a small flow. Other questions? Great. So one important thing which is different in the algebraic setting compared to the Boolean setting is that this computation is very syntactic. So in the Boolean case, for example, if you are working over f2, yeah, then x square and x are the same function, right? Because if you substitute x square x equal to 1, then x square and x evaluate to the same value. If you substitute it equal to 0, again it evaluates to the same value. So as a function over 0, 1, they both are exactly the same thing. But as polynomials, they are not. Yeah? X square minus x is not a 0 polynomial even on f2. Yeah? And so because these objects are syntactic in nature, one expects that there is a little more structure when we compute things syntactically. Yeah? And therefore, there is a little bit of hope that we can prove lower bound for such models of computation. Yeah? It becomes a bit harder if, you know, it's functional, but if it is as syntactic as an algebraic circuit is, then we hope that maybe because of this extra structure, we may be able to exploit it and prove lower bounds. And the other difference is, of course, that we are allowed to work over any field of our choice. Most of the time in this whole discussion, we'll only talk about complex numbers, but maybe we can talk about other numbers. So let's see what comes up, right, in a discussion. Okay. One more definition here. We'll say a polynomial is homogeneous if every monomial in it has exactly the same degree, and correspondingly the model of computation, maybe circuit or formula, is homogeneous if every gate inside it computes a homogeneous polynomial. Okay, so let's go back to the example we saw on the first slide, this polynomial which adds all monomials of all degree, right? That's not homogeneous. Yeah, it adds monomials of all degrees. But now I'm going to tell you very typical examples that come up in algebraic complexity. Yeah?
Is it possible for a non-homogeneous circuit to compute a homogeneous polynomial?
Very good question. The question was, can inhomogeneous circuits compute homogeneous polynomials? Yes. In fact, on the next slide, we'll see such an example where inhomogeneous circuits can do wonders sometimes. Yeah? So, yes, very good question. Yeah.
What is an inhomogeneous or a homogeneous circuit?
A homogeneous circuit is a circuit. Sorry. Homogeneous circuit is a circuit where every gate inside it computes a homogeneous polynomial.
Oh.
Yeah. So it's yeah.
Yeah, what's a homogeneous polynomial?
A homogeneous polynomial is a polynomial where every monomial has the same degree. So like summation xi is a homogeneous polynomial.
Can we just squish that into a coefficient then?
Not really, because these are actual variables. So, for example, I give you a polynomial x1 plus x1, x2. What are you going to do with it? It has two monomials, they have different degrees. Yeah, it's an inhomogeneous polynomial. I mean, we don't dislike inhomogeneous polynomials. We can have them all. Yes. So here are two classic examples. If you take back nothing from this course, if you take back the definition of these two, I'll be very happy. These are two very important polynomials in algebraic complexity, the determinant polynomial and the permanent polynomial. The determinant polynomial should be more or less familiar to most of you, because we all know how to take determinants of matrices, right? So if the matrix, instead of having constants in it, had variables, every I, j entry of the matrix was a fresh variable xij, yeah? Then the determinant, if I just write it out as a whole, monomial representation, it's basically going to look like this. Yeah? It's going to be like this times determinant of this minus this times determinant of this, and then you keep expanding each determinant, and you get like this huge sum with signs. Yeah? But if you throw away the signs, you get another polynomial called the permanent polynomial. And if you notice, like monomial by monomial are exactly the same except for the sign. Yeah? So these are like two very classic polynomials that we like to study in algebraic complexity. What's known about them? So if I ask you to take a guess about determinant, most of you are going to say, yeah, it should be easy to compute. Yeah, because we all know that Gaussian elimination is easy. So we all know that there's a very simple algorithm, at least like the normal algorithm that we know about, right, before this lecture. So if efficient computation in algebraic complexity maps to efficient computation in Boolean complexity, which it better, otherwise the field has no meaning in some sense, right? So, and it does. So you would imagine that the algorithm, maybe not exactly the same algorithm, but there's some algorithm that gives an efficient upper bound for determinants, and it does. So we know that there are polynomial size algebraic circuits that compute the determinant. This is well known. Okay? But what about the permanent? We don't know. Nothing.
We know that it's P-sharp complete.
Sharp-P complete, exactly, right? If you look at it functionally, it's Sharp-P complete. So what's your intuition then? Should it be computable by small size circuits or not? No, right? Yeah, exactly. Yeah, we really believe that it shouldn't be easy to compute, but we don't know how to prove this today. Yeah? That's in fact the big VP versus VMP question. Yeah, you may have heard about it somewhere or in some popular literature or something like this. Yeah?
What's the V?
Yeah, good question. So this is a bit like P versus NP, right? So it's the algebraic analog of that. It was defined, these classes were formally defined by this person called Valiant, and then somebody else, not himself, decided to put the V for Valiant in this. Yeah, sometimes complexity classes have weird names, like, I don't know how many of you know what NC stands for. Next class, yeah. SC, anybody here? SC, Steve's class. Yes, Rani would know, but yeah. Okay, so this is like Valiant's classes, if you want to call them that. I don't think anybody says that anymore, but VP versus VNP. This is the question of, can permanent be computed by small size circuits or not? That's the question. So now after this slide, you know like the biggest question in algebraic complexity. Yeah.
Can we think of it as like P poly, but with these algebraic gates?
VP, you can think exactly like this. Yeah, VNP is like some sort of a there exists version of this. Yes? Okay. So let me show you another polynomial and another very nice upper bound for this polynomial. Okay, so what I said so far is one of one of the polynomials we saw was on the very first slide, this polynomial which was inhomogeneous, right? And it had a small circuit when you went to sigma pi sigma. Then the determinant polynomial, then the permanent. On this slide, I tell you about one more polynomial. This is called the elementary symmetric polynomial. Yeah, it's a lot like the first polynomial we saw, except now I only add monomials corresponding to those sets which have cardinality d. Yeah, this is an elementary symmetric polynomial of degree d. All right. Of course, the size of this circuit is huge. This is a monomial representation. It's n to the d, yeah, or n choose d if you want to be precise, right? But of that order. Now I'm going to give you also the answer to the question about inhomogeneity and a very nice upper bound for this polynomial. Okay, so let's look at this polynomial for a bit. Yeah. So this polynomial in red, yeah, it has n plus 1 variables. It has all the original n variables and this extra variable t. Yeah. If you think of this polynomial as a polynomial which is univariate in t and has coefficients from all these polynomials on x1 to xn, then you can easily observe that the coefficient of t to the d in this polynomial is in fact the elementary symmetric polynomial, right? And then this seems to have a very simple circuit as well. Yeah, it's a lot like that circuit I showed you on the very first slide for that other polynomial. It's inhomogeneous, note. Yeah, because these linear forms are inhomogeneous. They have degree 1 and degree 2 monomials. Degree 0 and degree 2 monomials. So, however, we do not know how to pull out the coefficient of this, right? Anybody familiar with an idea that allows you to pull out a coefficient from a univariate polynomial? So I tell you that this is a univariate polynomial. Figure out what's the coefficient of degree t to the d. Anybody has seen this trick before? Maybe not, which is fine too.
Take derivative.
Yes?
You differentiate d times, then you evaluate at 0?
This could work, yes.
That's not okay.
Yeah?
Interpolation.
Interpolation. So some of you may have already seen this before. It's kind of quite natural as a trick. So what one could do, right? Where am I? Yeah. So interpolation just means that for this, in the place of t, I just substitute constants from a field. So imagine I start substituting alpha 1, alpha 2, alpha n. Okay? So I take this red circuit and in the place of t, in one of the circuits I put alpha 1. In another circuit I put alpha 2. Yeah? I make n copies of this little circuit, and in each one of them I substitute a fresh variable, a fresh constant for t. Okay? Then it's not so hard to notice that the following structure emerges. I guess this matrix should be like square or something. Just forgive me for some +1, etc. errors. And I'm not writing E sim, but it's like E and N1, I'm going to say, or N0, I guess. And this is that red circuit with alpha 1 substituted. So, red circuit with t equal to alpha 1. I'll explain if it's not yet clear. And so if you look at the first row, Yeah, it's the evaluation of the red polynomial at t equal to alpha 1. Yeah, and if you actually evaluate it and open it up, it looks like this polynomial, the inner product of this with this, right? The coefficient of the term 1, so maybe I have to say a bit more. Let's open up this polynomial. Tell me if it's not clear. I hope it is. Yeah, let's try to analyze what's the coefficient of alpha to the 3, let's say. Yeah, coefficient of alpha to the 3, alpha 1 to the 3. What is it? It's elementary symmetric polynomial of degree 3. Yeah, let's look at what is the coefficient of alpha 1 to the square. Yeah. In this huge product, you have to take this term twice and 1 everywhere else. Yeah. So it's basically all the things that you can form by taking this twice. That's elementary symmetric polynomial of degree 2. Yeah. So essentially what I'm trying to say here is that take any row of this matrix, inner product it with this, that's this polynomial. And then so on. Yeah?
Where do we get alpha?
These are like constants from the field. I am allowed to choose any constant from a field. All of them should be distinct. This is also to demonstrate that because we are working in an algebra, we are not bound to the 0-1 kind of fields anymore. We can take large constants if we like. All of them from some field. Okay. Yeah. So now what happens is, I already know how to compute these red circles. They are easy to compute. Yeah. These are only constants. Yeah. And in fact, this matrix should look familiar to all of you. This is like the Vandermonde matrix. Yeah. It's invertible. So it has non-zero determinant. So I just invert it. Take it to the other side. Yeah. And then I can pull out any elementary symmetric polynomial I want from this. Yeah. It's a beautiful trick. I think I'll say this line again now, which I said a few minutes ago. If you take back nothing from this 3 lectures, I think this is one trick you should definitely take back. This is a very beautiful trick. This is like one of the first things people learn in algebraic computation. And it shows the importance of inhomogeneity, for example, shows the importance of working over large fields, for example. Yeah? So essentially, one talks about this trick as follows. It's always easy to say that from now on, anytime you want to do interpolation, it's substituting values for the unknown enough number of times and then taking some linear functions of those. That's all it is. Yeah. You know.
It's a bit of a vague question, but so if you see a result in algebraic complexity and they say it holds over large fields, could you guess that they probably done this?
Good question. So the question was, if you hear that this result holds over large fields, for upper bounds, it could be interpolation, and it could be like 5 other tricks that I know, and some other tricks that people keep coming up with. Yeah. So there are algorithmic tricks that make you compute things efficiently if you go over large fields. Interpolation is one such algorithmic technique. You'll see 2 others in this 3 lectures. Yeah. So there are these 5 tricks I know that make you work over large field. For the lower bounds also, sometimes we say this only works over large fields or only works over. This comes up also because of algorithmic constraints. Often, yeah. Right?
In this trick, you can work over an extension point, I guess.
Yeah.
So
You just need large enough, yeah.
Yeah.
So you could work over like f2 to the cube or something. That's true. So here you can make characteristic quite small while the field size large. Some of the things just need large constants. So in that case, it's harder.
So usually, so let's say your base field was actually like f cube. but you need to go to some fq to the m in order for this to work. So then you can sort of simulate, because fq to the m is a vector space over fq, then you can simulate and still get something
That's
good.
Yeah. Yes?
And did you call this trick interpolation?
This trick is called interpolation, or sometimes also referred to this as Benot trick. This was the person who invented the trick first, I think, as far as we know, but it's really interpolation, so it's hard to say that. You can't really go ahead and say that it was invented, but it was discovered in this setting. Is this trick clear to most of you here? Yeah. You can go over it later. I'll share the slides, of course. So, and coming to the point of inhomogeneity, this was one place where the final polynomial you intend to compute is homogeneous, but intermediately you've used some inhomogeneous computations which will cancel out in these linear, when you put together the linear combinations of those. So it does seem to help. In fact, we do not know whether there exist small formulas. So here it can be thought of as a simple formula actually, and it's a depth 3 formula of polynomial size that's inhomogeneous, but we do not know whether there are homogeneous formulas for elementary symmetric polynomials. This is a very interesting open question. So come up with a formula of polynomial size that's homogeneous for computing elementary symmetric polynomials. We don't know how to do that. For d small, you can do it. Yeah. So there is a paper by Rubesh and Yehudev that does it for small d, but for large d, we don't. Imagine d is like n by 2 or something. No idea. Yes?
What do you think the answer is?
What do I think the answer is? It should be hard, but I don't know. It was conjectured to be as hard as like the hardest thing, but that was proved wrong by this Rubesh and Yehudev paper, and it was shown that for small degrees, you can actually do something better. Yeah. But I think for large degrees, it should be hard in my view. We just don't know how to prove it. Okay, great. One more definition through. So what did I do so far? Circuits, formulas, some nice examples, how to use inhomogeneity. Now I'll tell you one more definition. This is the third model of computation that we often talk about. This is called algebraic branching programs. Yeah. Anyone here seen Boolean branching programs, like branching programs in the Boolean world? Yes. And maybe like OBDDs or something like this. No? Okay. Anyway, it's a very simple model. Nothing. You don't need to know anything before this. Yeah. Just helps if you know something before. So, what is an algebraic branching program? It's a directed acyclic graph. Two designated nodes, a start node and an end node, S and T. Then you have all these DAG edges going from source to sink, layer by layer. And every edge carries a linear form or affine form on it. Yeah. So affine form, somebody was, I think you were asking, right, about affine forms feeding in. So here actually we just allow affine forms on the edges. And then the computation is done as follows. When you go from S to T along a path, you encounter a bunch of edges. You just multiply the weights on these edges. Weights are just these linear forms, as I said, and you just multiply them out on every path. And the polynomial computed by this entire structure is the sum of all these. Yeah, so if you've seen Boolean branching programs, it's just the algebraic variant of it. If you have not seen it, then before you internalize the definition, let's just look at an example. That will just help you immediately, it will just click. Yeah. So this is an elementary symmetric polynomial of degree d. We already saw this object. I want to compute elementary symmetric polynomial of degree 1 using a branching program. Okay, what is an elementary symmetric polynomial of degree 1? Summation xi. Yeah. I just want to compute it in a branching program. And as you can see, I'm not very good at TIC-Z, so I have a handwritten picture here. Okay. So let's see how this computes that polynomial. Okay. Start from S and trace the top path here. They're just all ones. Okay, so that's one of the paths reaching here. That's one of the paths reaching here. It has weight 1. Let's look at all different paths that are reaching here. So here is another one. It has weight x1. What about the second path? Has weight x2, and so on. The final path reaching T is this one. It has weight -1. So you had a weight 1 path, then x1, x2, x3, etc. Yeah, weight of the paths, as we discussed, is computed by just taking multiplication of the weights on the edges. And then, what is the polynomial computed by this? It's just the sum of all the weights of the paths. So in this case, it's summation xi. And in fact, now you can create branching programs using like this branching program and another one, and like multiplying them out nicely to create branching programs for elementary symmetric polynomial of degree 2, degree 3, Yeah, it's quite easy to do that. Of course, if I allow linear forms on the edges, then I could have just added one edge and put summation xi. But I wanted to do it like this so that you can now generalize for degree 2, degree 3, and so on. Question?
When you take the path, you multiply all of the weights?
Yes, precisely. So in this case, for example, let's take this path, 1 times x1 times 1, 1, 1, 1, 1.
Right. So why is it -1 for the case where
for the last one? Because you know I had to add this one path, so it's like just a hack to remove that, yeah.
Okay.
Make sense?
I guess part of the definition of polynomials, we never have constants on their own.
On the?
On their own, the coefficient, like x to the 0.
Yeah, you can have them. You can have them. Yeah.
You can?
Yeah. Even in the circuit, I think somebody asked this question, right? Where are the constants being fed? You can use whatever constants you like, even then. You can use like -1s and minus infinity, not infinity, minus pi or something. Questions? So branching program, that's the model is clear? Yes? Okay. So we just have these 3 models, more or less. That's all we need to talk about. Yeah? Circuits, formulas, branching. That's it. Questions? Yeah. So let's try to understand how one can convert one from the other. Or can we do efficient conversion between these models of computation? Yeah. So what this lemma is saying is that if you have an algebraic branching formula of size s, you can convert it into a branching program of about the same size. So branching programs are at least as efficient as formulas are. So rather, branching programs can simulate formulas. The second line says that the circuits can simulate branching programs. And I will do, yes.
I'm sorry, what is exactly an algebraic formula? So it's found out 1?
Yes.
Oh, all right. Okay.
It's a tree, yeah.
Yeah, it's a tree.
Fantastic. So I'll just do the proofs now. And the proofs will be by pictures. The pictures will be by hand. I cannot draw them. Okay. So inductively, assume that you have like branching programs for these. Okay, and I just want to create a branching program for plus. Put them in parallel. No big deal. For multiplication, just put them in sequence. That's it. Yeah, that's the proof for the first one. Very simple. What about going from branching programs to circuits? Also easy. Let's assume this is my branching program. I inductively have circuits for everything up to this layer. I want to compute something on the next layer. Yeah? And we allowed that these have linear forms or affine forms. What do we need to do? Whatever is the circuit computed so far, we need to multiply it with this whatever is computed so far, we need to multiply it with this, and then we add them together. That's it. Just do it for every gate on this layer, or every node on this layer. You'll have one gate. You can, of course, reuse G1 because you're computing a circuit now. So you can always reuse stuff. Yeah?
So that's not a tree.
This is not a tree. Yeah? In fact, that's a very great question. Can we simulate this by a tree of small size? We don't know. Makes sense, right?
Is there some reason to expect we shouldn't be able to simulate it by a tree?
Yes. Pretty good reason. I'll tell you shortly. Yeah, all good so far? So, actually one other conversion is interesting, so I'll just tell you about it. You can go from circuits to formulas efficiently. Only if you have constant depths. Okay? So imagine you have a circuit of size S and the depth is constant. Yeah? That means you have this DAG-like thing, it has, every node has large fan-outs and so on. Your task is keep the depth the same, but open it up into a tree. Yeah? From simple graph theory, we know that if you open a DAG into a tree, the blow up in size is size to the depth. Because for every node at a layer, you just need to copy everything under it a bunch of times, and a bunch of times, and a bunch of times. Right? In the worst case, you will copy the original gate S to the delta many times. So that's trivial. And this is a reasonably good upper bound if delta is a constant. So if your polynomial is computed by a circuit of size S and order 1 depth, then you have a formula for it of polynomial size. So within constant depth, we will not distinguish between formulas and circuits. They are the same. Yeah? So when I say something about constant depth in this discussion, I'll interchangeably, sometimes erroneously say formula and circuits, but it's all the same. So I'm not making any error per se. I may misspeak when I want to say formula. I may say formula, I may say circuit, but it's all the same at constant depth. Not the same at higher depths. Okay. Large depths, we don't know. Yeah, as we already talked about. This is in fact the other open question, like the VP versus VMP is a similar type VF versus VP question, and we are going to talk about it shortly. So in general, the question is, can formulas be efficiently simulate branching programs? We do not know. Can branching programs simulate circuits? We do not know. What does efficiently mean here? Like with polynomial blow-ups. Okay? If you allow for slightly more blow-ups, something is known. We'll also talk about it shortly. Okay.
So VNP, if we try to look at the Boolean parallel, then VNP is like Shafi.
Yes.
And VP is, I guess, something even below P.
Yeah.
What is VBP?
VBP is like sharp L. I don't know whether you know this.
Sharp L, no.
Yeah.
Counting
Counting number of paths in a graph, like this is kind of,
okay.
it can encode that. Yeah. Sharp L.
And VF?
VF is like sharp NC1. That's right. All good?
Why is VF with sharp NC1?
Why is VF sharp NC1? So you can always formula depth reduce.
For VF?
VF, yeah.
So we have to what's the depth here or other?
So in general, the formula can be arbitrary depth, but we can depth reduce it with polynomial blow-up. So now it's like log depth. You can assume without loss of generality it's log depth, and then it's just like counting.
Yeah, but also for the log depth you can have like a arbitrary value, right? So it's more like a VAC one or something?
Not really, because you can just assume at log depth that the and Fanon or like the times Fanon is true.
Okay.
And that's kind of complete for yeah. Yes.
Sorry, are we like imposing some uniformity condition in all this discussion?
No. This is like slash poly everywhere. Yeah,
Okay.
yeah, good one. So it's like sharp P slash poly is VP. I take that back, but yeah, slash poly everywhere.
Okay.
Yeah, sorry. Other question? So now I'm going to present the part where I tell you all these classes. But before that, one nice photo of a pleasant person called Valiant. Pleasant looking person. I've never met him. I'm sure he's pleasant. There's a very nice paper from 79 that Valiant wrote that kind of kick-started this complexity of polynomials area. And what he did there was he defined complexity classes for polynomials that we will talk about just after this slide. He defined the notion of reductions, like in the Boolean case we have, right? SAT is complete for NP. What do we mean by that? Every problem in NP reduces in polynomial time to SAT. So what's a similar notion of reduction in the algebraic case? Yeah, and how can we show certain polynomials are complete for these classes? This kind of stuff, right? So he formally did these things in this paper. It's like a typewritten paper because it is from 79, but it's like a very modern paper, written like we write papers today. So it's very accessible, really nice to read actually, and quite a path-breaking paper because it started some of these lines of work. Yeah. He recognized that there is this very nice connection between Boolean circuit lower bounds and algebraic lower bounds, and also noticed that maybe studying algebraic lower bounds could be an easier, more tractable question, and that's how a lot of the work started. So now I'm going to tell you about these classes I've been talking about. There are 4 classes we'll study, and I'll share the slides, so if you kind of your energies are draining out, then let me give you like a TLDR version of this. Everything computed by polynomial sized formulas is VF. Everything computed by polynomial sized branching programs is VBP. Everything computed by polynomial sized circuits, more or less, is VP. There's a little caveat. And like a there exists version of VP is VMP. Okay, so this is what I'm going to say now more formally in the next 5-10 minutes or so. Yeah.
Wasn't there a 5th one?
Was there a 5th one?
I think in the paper it said 5.
Okay, I'm going to show you one picture at the end of this. So I'm going to introduce a 5th one, but Valiant did not. I'm going to tell you about it. Yes. Right. So let's start. So now it's a little bit more formal, right? So VF is a family of polynomials. As in the Boolean case, we have to define it for a sequence. So one has to talk about it like this, right? So a family of polynomials is said to be in VF if there is a polynomially bounded function, say S, such that this polynomial for every n can be computed in size S of n. So like I said in the TLDR version of it, right? Polynomial size formulas.
And just to make sure reference of degree n.
No, not degree, but number of variables.
Oh, okay.
Degree could be related to n as polynomial. If not, we have to specify this as a family with 2 parameters. Let me just keep it simple for this definition. It can be done quite straightforwardly. Examples. determinant of a Vandermonde matrix. Yeah? Has anybody seen the expression for this? Yes?
Product of
whatever, I naught j, right? Alpha I minus alpha j. Right? Sorry, your question, you had a question? No. No? Sorry, did you ask a question? Did I miss something? And this is a small formula, clearly. Yeah, so its determinant has a small formula.
Maybe I less than j?
I less than j, right? Yeah, I thought I was making some mistake here. Is it? Yeah, less than j. But it's small formula, right? Now I'm going to introduce another polynomial called iterated matrix multiplication polynomial. This is going to be an example for us. So what's this polynomial? You have D matrices, yeah, x1 to xt. Each has a fresh set of variables. Okay, so there are, and it's say n cross n matrix. So there are two parameters I use here, n and d. Yeah. There are D matrices, and each is of size n, right? And there are fresh variables here. Let's say the variables here have superscript d. So ijth variable here is x superscript d ij, and so on. So fresh variables. You multiply them all out, and you get this matrix. And iterated matrix multiplication, let's say, is just 1, 1 entry of this. You can actually choose any entry you like, but let's say 1, 1 for concreteness. All good? So, interestingly, if the matrices are small, all say 3 by 3 matrices or something like this, but really any constant by constant matrix, square matrices, let's say, D of them, then this polynomial is actually in VF. And if somebody is familiar with this NC1 type algorithm, it's just divide and conquer. It will just show you that there is this. You don't need to be familiar with it, but it's exactly that. Yes? Okay. So VF introduced. What about VBP? Same logic again. Polynomial families that have polynomial sized branching programs. Examples, if you don't stay within Vandermonde determinant, but take generalized determinant, like the polynomial I introduced in the very beginning, the classic polynomials I called them. That is in VBP. Yeah, it's not so straightforward to see the upper bound of VBP for that polynomial, but there are very clever constructions that show that it is in VBP. I highly recommend reading the construction that is in the paper by Mahajan and Vinay. It's very beautiful. Other polynomial families like IMM that we saw, or elementary symmetric polynomials, they are all in VBP. They have polynomial sized branching programs. Okay? Good. What about VP? VP is polynomial sized circuits. All polynomials that have polynomial sized circuit. The only caveat is like an example like this, or a non-example like this. Let's go back to x to the 2 to the n. Yeah? By repeated squaring, this has a polynomial sized circuit, but this is not in VP. Yeah? We actively exclude polynomials that do not have polynomial degree from VP. This is only to make it coherent with the Boolean setting. Yeah? Because you want that when you have a polynomial sized circuit and you substitute 0, 1 values for input variables, you want to compute functions that are like write downable efficiently. Yeah? So the output representation should have polynomially many bits. That's kind of why we are doing all this. So the VP is defined to be like this, just to make it like coherent with the Boolean case. Yeah, otherwise you are computing functions which are like super difficult to represent. Polynomial bits do not suffice. So we actively exclude such functions from VP, but well, most polynomials we've seen so far, like determinants and IMM and everything, has polynomial degree.
Wait, what do you mean that a function is not write-downable? Because like, I mean,
the output is not write-downable. So,
oh, okay.
Yeah.
Because I'm being a bit pedantic by saying that the circuit itself is
it's a representation for the function, agreed. But the point is that, you know, you want to compute things that have bit representations that are tractable for it to make sense in the Boolean case. And yeah.
When you say in the Boolean case, you mean real input, but like an integer input, but then we want to write it down as a bit string?
Yeah. Yeah, exactly.
Because also some of the tricks that we are seeing, interpolation and things you'll see, also like those things are more coherent once you're working with polynomial degree.
Definitely, definitely.
So for the VP, can the intermediate polynomial have like a superpolynomial degree?
One more time?
So can the intermediate polynomial, say like I take a node, can have superpolynomial degree?
No.
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 Okay.
Throughout we assume that every gate computes a polynomial degree polynomial.
So it's a syntactic restriction.
It's a syntactic restriction. Yeah, so that's why it makes it a bit difficult for VP to have like complete polynomials. We don't know any good candidate complete polynomials for VP.
I see.
But people just say determinant, you know, they just work with that, and that's actually in VBP. Okay. So it's 3 p.m. With a show of hands, anybody wants a break for 5 minutes? Yeah, I think a room without windows needs a break. Let's take a 5-minute break and then. Alright, so the next class and the final one that we'll introduce in this course, which is VNP. VNP, like I said, is like there exists P. So how do we define this there exists P? We say that for a polynomial, for a problem to be an NP, there should be like a polynomial predicate that given original input and some witness computes this polynomial predicate and decides whether it's valid or not, the witness. It's kind of similar, kind of an arithmetized version of it. So how does it work? A polynomial is said to be in VNP if there is a polynomial in VP and some polynomial function such that the original variables and interestingly 0, 1 assignments to these new variables added together compute the polynomial. Okay? That's the definition. Often in many algebraic complexity talks, if you attend a talk, nobody defines it because the definition is a bit clumsy and it's not a very good working definition. So this may be the first time you have seen the definition and perhaps the last time you will see it. But I have added an exercise for you to get a feel for it if you want to. For example, let's look at an example of the permanent. I had written down what the permanent looks like over here from the previous slide. Imagine that I was able to write the permanent in the following way. Okay? I come up with a polynomial only on y variables followed by this kind of a dot product with xi xj. The polynomial f of y has the property that it evaluates to 1 over 0, 1 inputs if and only if y is a permutation matrix. Yeah. If y was a permutation matrix, what would it have done? When you do dot product with the original matrix x, it would have just picked up a permutation from x and added that as a monomial inside this polynomial. That's exactly permanent. Yeah. So if I'm able to write f of y as a matrix that evaluates as a polynomial that evaluates to 1, if and only if y encodes a permutation matrix, then I'm done. Yeah, and that's one of your exercises in the question bank if you want to think about it, that this can be done by a small formula. Okay. So in fact, it can be shown that permanent is in VNP. Yes?
In the definition, what's the intuition for summing over all y
Right.
instead of saying there exists?
Yeah, so there exists would be like a Boolean analog of this algebraic version, right? For example, for sharp P, what do? We say, tell me how many witnesses do you have? So you like add up all possible vertices, right? That's the kind of function you should have. So that's the intuition. I think that's the intuition. Yes?
In VNP, does the n mean non-deterministic?
In VNP, the n means non-deterministic, yes. It was like conceived as a thing which stands similar to n, has the same role as NP in the algebraic.
I mean, is this class defined to make sure permanent n is accounted for?
Yeah,
Or like,
indeed.
or was it the other way around?
No, I don't know. Yeah, I don't know. I don't know what Valiant was thinking, but it's the perfect definition that capsulates permanent. I don't know.
Should it have been called V sharp P instead of VNP?
It's a good question. I would then put sharp for all classes. I don't know.
Oh.
Yeah. Yeah. And then now, if I were to say something is complete for a class, I need to tell you what a reduction means in this world. And the reductions are far, far simpler in the algebraic case. You say that a polynomial reduces to another polynomial, say f reduces to g, if g can compute f under some evaluations of its variables. So the variables could be substituted with, x or field constants, whatever you like, but overall it should be able to compute that polynomial. Yeah? So there exists a projection of its variables under which it computes the other polynomial, then it's said to be reducible. Let's quickly see an example because the definitions are often hard to parse. So I want to show you that this very simple polynomial, which is product of variables, yeah, this reduces to iterated matrix multiplication. Does anyone see why that should be the case? Recall iterated matrix multiplication was simply multiplying, D matrices of size n by n. And I'm saying here now the matrices should just be like 1 by 1 matrices, D of them. Yes?
Oh wait, the matrices are just the numbers.
Yeah, precisely, right? So the matrix is, first matrix is x1, second matrix is x2. Yeah, this is, I know, it's, yeah, but you now see one example of a projection reduction, right? These were matrices, they had x11 in the first matrix, x11 superscript 2 in the second matrix, these were the variables, but now I substitute variables from the original polynomial and recover it. Okay, slightly more interestingly, yes?
Here, instead of taking yi to be just a variable that we had before, what if we allow yi to be a linear combination of the xi?
That's fine, but
That's
then
fine
it becomes, the reduction becomes more complicated,
yeah.
And people have studied such reductions, which are linear forms instead of projections. But then what it does in circuit complexity language is that it puts one more layer of gates, right? Because you have to do this plus, you have to expend energy to do this plus. And we don't do that. I mean, you could also do it. People have studied these things, but for our purposes, we'll just keep it simple. But if that was allowed, then this was even more, like the second one would become quite trivial, right? Summation xi. Okay, so any guesses for this one? Now I want 2 by 2 matrices such that when I multiply them out, it actually gives summation xi. Yes?
Can you do like identity matrix, but you have the element that you want in, say, the top right, and then multiplying those matrices as in the top right?
It's a very good guess. We are going to do something similar, but there was another answer here. Yeah.
I mean, you just did it.
I just did this actually before. Yeah, it was that ABP example, remember? ABP can really be thought of as matrix multiplication, right? For 2 consecutive layers, it's an adjacency matrix. And I already drew an ABP for elementary symmetric polynomial of degree 1. Yeah? So to actually spell it out, it's exactly what the solution was being suggested.
Writing it down as the ABP makes it actually.
Writing it down as an ABP makes it more pictorial and more clear, I guess, but you could have just done this. Right? So if you just multiply these two matrices, you can quite easily see that this inductive structure of 1 along the diagonal and 0 here is preserved. And actually now you start computing x1 plus x2 at this entry. And then if you kind of do this repeatedly, then finally the 1,2th entry would be the polynomial of interest. And then maybe you have to do a little bit of pre and post computation to rotate this matrix so that it becomes a 1,1th entry. So therefore I said n plus a little bit of pre-post multiplication. Yeah, but is the idea of projections clear now? Yes.
Question.
Yes.
That last part, we need, which entry do we need? Do we get as our final answer?
I mean, if you are a little more relaxed about it, then any entry in the matrix is fine, to be honest. But if you really want like 1,1 entry of the matrix, then you have to do a little bit more work. Other questions? And so that's all done. Then we are ready to define what a polynomial, when a polynomial is complete for a class. A polynomial is said to be complete for a class is exactly like Boolean setting now. That the polynomial is computed by that class, and every polynomial computed by that class reduces to this one. That's it. It's exactly like NP hardness. And so, by previous results, we know that permanent is complete for VNP. Yeah? It requires work to show that every polynomial in VNP reduces to the permanent. So, that's what, among other things, Variance paper did. It's beautiful gadgets and so on if you are into those kind of things. Determinant is complete for VPP, and IMM 3,n is complete for VF. So we kind of argued a little bit about the upper bounds, not quite for determinant, but yeah. So all these are known to be true.
What about VP? Do we know?
No, we don't have any nice polynomials complete for VP, unfortunately. That's something I spent a lot of time on with not so much success. Yes?
Why 3 for VF? Is it kind of the same reason why 3 sat is harder than?
No, not quite, but it's a very interesting question you asked. So, of course, for every constant, IMM constant comma n is in VF. That just by, we discussed divide and conquer. But why is it that every polynomial here is computed in this? So, if you've seen Barrington's result for Boolean case, every polynomial, every function in NC1 has width 5 branching program. It's kind of exactly the same in the algebraic setting. Benor and Cleve showed that any polynomial computed by a formula of polynomial size has a width 3 ABP, kind of like branching. It's a very beautiful paper again. All right.
I guess there's an interesting observation that, IMM 2,n, there are even polynomials that it can't compute.
Exactly, yeah. So if you go to, the comment being made here is, if you go to 2 by 2 matrix multiplication, yeah, then in fact, it's known that this model is not even complete. In fact, somebody in this building or the adjacent building has proved this. Eric Allender and Wong proved that there are very simple polynomials on just 16 variables or something like this that cannot be computed by 2 cross 2 ABPs. Just can't be, like this model is not complete. But at 3 cross 3, not only is it complete, but can do everything that formula can do. It's quite interesting. And now there are new results that say that in the border computation, which I'm not going to define, 2 cross 2 can also do everything. But anyway, that's another thing. All good? So far, so good? So we have this nice picture now. VP is contained in V and P. We didn't quite argue this. This requires an argument, but now with this definition, it should be quite clear, right? Just don't have these Y variables and you can observe it quite trivially. Of course, we do not know whether VP is equal to VNP or not. That's a big open question. Why should everybody else care about it outside of algebraic complexity? Well, like I said, algebraic complexity sort of provides a first step towards Boolean lower bounds, perhaps. This can be made more formal by the statement of Bergeser that if P is not equal to NP, then in fact VP is not equal to VNP. So in other words, if your life goal is to prove that P is not equal to NP, let's say, then you may be tackling an easier, potentially easier question by trying to prove this. Because this in particular is implied by P not equal to. So that's a reasonable reason to try to look at such questions, I guess.
Is GRH study?
Yeah, somebody read this part. I was hoping nobody asked anything. Okay, this implication holds only under assuming generalized Riemann hypothesis. But I mean for finite fields. So let's say we are working over finite fields. Then this is known. You don't need any GRH. For complex numbers and so on, you need GRH. But for say FP, polynomials are over FP, then this is without GRH. Okay, just so I mean morally it's correct. And now I sneak in this weird class in. So this is all the classes we saw, and then there's like a little class inside all of it. This is VAC0, I want to call it. It's not really defined in the literature, but these are all polynomials computed by constant depth formulas or circuits, like we saw. Circuits and formulas are the same at constant. Yeah, so this is like the whole picture of complexity classes inside VP and K. Okay, I'm going to now change the deck of slides and go over to another set of slides here. And that was the plan. That was supposed to happen at 3 p.m., but I have clearly overshoot. So give me 2 minutes to make the switch. I always start with very high, very ambitious plans. And as time progresses, I realize my plans are far too ambitious. So I started out making really good slides. And then I realized if I continued doing that, I wouldn't have a slide deck by the time I'm here to present. So I started writing things down. So yeah, I'm super well prepared here. But anyway, so now you have to bear with my handwriting here. The rest of the slides are handwritten. I hope they are still readable. But I'm right here, so you can ask me. So the last part that I want to tell you about today is some structural results that are very useful in algebraic complexity. Okay, so what we saw so far is we introduced the models of computation. We saw some very natural set of polynomials which keep coming up in this study. And then I told you a bit about the connection from algebraic to Boolean circuits and lower bounds. So finally, I want to just talk about some structural results. So what do I mean by structural results? So what I mean by this is I'm given a general circuit, let's say. Yeah? Say it's like inhomogeneous or something. But it's computing a homogeneous polynomial. Yeah? Or it's computing some structured polynomial. The question is, can I make the circuit also equally structured? Okay? This is the kind of questions we want to address when we talk about structured polynomials. Yeah? This is like saying that, do I have an efficient way of dealing with the current model of computation so that once I do this efficient conversion to this more structured model, maybe proving lower bounds there will become easy. Okay? So if this is a class of class of circuits that's computing this class of homogeneous polynomials, can I convert it into, say, a very small depth homogeneous circuit? Because if I were able to do that efficiently, I may be able to prove lower bounds for this kind of circuits. Okay? So by making structural changes to circuits, we may be able to compute something, we may be able to prove lower bounds better. That's one of the reasons. Another reason is just we understand the algorithm better. So for example, we have this conference called SOSA, right? You have very convoluted or sometimes very intricate algorithms that people come up with. But then somebody many years down the line notices that, okay, the same algorithm, same task can be done by this very simple algorithm. Yeah? It has many reasons, one has many reasons to do this. One, because the algorithms just become simpler, they become easier to understand. Once you have an easy to understand algorithm, maybe proving lower bounds becomes easy. Right? So it's coming from this philosophy that can we make circuits more structured. Okay. So, what kind of structure? Yeah, for example, homogenization. If the final polynomial I'm trying to compute is homogeneous, can I make my circuit homogeneous? If the final polynomial I'm trying to compute has some structure, can I make the polynomial, squish it down and make it depth reduced circuit? I wrote a few more down, but we'll come to them as we go. Yes?
Why are homogeneous circuits so important compared to
I wouldn't say they're important. They somehow came up a bunch of times in today's discussion, but they're just like one of the different structures circuits have. Okay. And I don't think they're like by themselves super important, but for example, people have been able to prove lower bounds for homogeneous formulas in the past. And so, it seems like a restriction where not only can we mold circuits into that restrictive form, we can also prove lower bounds for that. So maybe that's one reason, yeah. But yeah, I don't want to give too much importance to this one concept, but yeah, very interesting tricks are known in this case. So maybe that's one of the reasons why I'm talking about it. Yes. So some notation here going forward. So we'll have capital N many variables throughout, unless stated otherwise. We'll work over fields of characteristics 0, let's say complexes, unless stated otherwise. And I have this weird thing of saying circuit as CKT. I don't know why I do this. I do this all the time and it confuses people. But yeah, please don't be confused. Okay. So let's talk about homogenization. Suppose I have a polynomial f that is homogeneous. That is, all its monomials have the same degree. Then, in fact, it's known from previous results that you can always come up with a circuit or an ABP that is also homogeneous without too much blow up. The blow up is only order d square times s. Is the statement clear to everyone? Starting with a homogeneous polynomial which doesn't necessarily have a homogeneous circuit, you can always convert it into a homogeneous circuit. If you started out with inhomogeneous ABP, with about the same blow up, you can also make a homogeneous ABP for the same. Okay. And I'm going to tell you the proof. It's quite easy actually. Yeah. The proof is that you just try to compute each degree D component separately. Yeah? And just inductively keep building these degree D components. That's really like a one-line idea for this. Okay, but let me do a proof by pictures again. So suppose you had these two gates G1 and G2, and inductively I computed all degree components of G1 and all degree components of G2. Then to compute degree I component of G, and if G were a plus gate, then I just add these two. Because addition gate doesn't change the degree in any case. So for computing degree I component of my current gate, I just need to put together the degree I components of its children. Multiplication, it's like convolution. That's like a one-word proof for it. Yeah, because if you have to compute a degree I component for your final gate, you can take degree 1 and degree I minus 1 component, and then degree 2 and degree I minus 2 component of its children. Put it together. That's basically like the convolution operator for the children, right? and you can do that. Super simple. That's it. That's the whole proof. Yes?
Is it work also for formulas, or?
Very good question. No. So the question was, does this also work for formulas? The answer is no, because you know, G1 comma J, if you started out, even if you started out with a formula, you could use some of the gates many times. Yeah, because even in this gadget right here, yeah, so just requires a little bit of thought, but it doesn't work as a formula. The same gate could be used many times, even if you started out with a formula.
So does this construction not work, or do we not expect any construction to exist?
Yeah, we do not expect any constructions to exist even. I would go ahead and say that, but it's a bold statement from me actually. So it's being recorded, so I don't know. But yeah, one does not expect perhaps. And elementary symmetric polynomial of degree n by 2 is an example. And I do not know whether one can come up with a homogeneous formula for this. But we do have inhomogeneous formula. So if it worked, it should work for this example. One moderately interesting thing to think about here is that the fan-in of every gate here is at most D now. Yeah, because you just don't compute high degree components anymore. There is no reason to. The final polynomial has degree D. Intermediately, in that strange computation we had for symmetric polynomials, for example, you computed some very high degree terms intermediately. But you don't need to keep track of them. They are anyway going to get cancelled. Some caveats for this construction is that the depth of this construction, even if you started out with a depth 3 formula, let's say, or depth 3 circuit rather, even then the depth of this homogenization just becomes huge. Yeah, because you need, for every degree D, you need one layer of gates. Yeah, because at the bottom layer you'll have all degree 0 and 1 gates. Then next you compute all degree 2 components of all the original gates, then all degree 3 components and so on. So the depth sort of blows up as much as the degree. And also it requires a little bit of thought, but you will figure out quite easily that it won't work for formulas. So I haven't added this as a question, but I think it's a nice question to think about to convince yourself that actually this doesn't work for formula. Yeah. But you can do something in bounded depth. Okay. So it's a, like I said, it's like a lot of words there. But I would concentrate on things which are sort of underlined and the title of the slide. So it says you can do bounded depth homogenization. So one of the caveats you can bypass. So if you started out with a formula or circuit of bounded depth, without blowing up the depth too much, you only blow up the depth twice, you can actually homogenize the circuit. Yeah? There is a blow up. It's not polynomial size circuit that you obtain, but the blow up is small in the size of the circuit, but large in the degree of the polynomial. It's a bit weird. It's like a parameterization result. Yeah? So, you know, in parameter complexity, you have these upper bounds where you have polynomial here, and like in the terms of the parameter, it's like a large growing function. So it's like a parameterized upper bound here, where the parameter is degree. Okay. This is, I'm just like telling you a result. I've not told you the proof, obviously. So I don't expect you to suddenly start remembering this, but I hope you kind of internalize the construction for homogenization of the circuit that we sketched on the previous slide. Yeah?
Do we expect such a thing to hold in characteristic P?
Very good question. So I don't know. So there are no bottlenecks, but there are no upper bounds. Yeah. Forbes result.
Okay, so then two things. Then
Yeah.
one thing, in one of your papers, don't you have some barrier against proving Newton identities?
Yes.
For,
Yeah. So
what is
I can say both the things. So over the small characteristics, we were able to show that, I mean, okay, there is one way of doing homogenization, which is through Newton identities. And we were able to show that on small characteristics, these Newton identities will not work.
Yeah, but they could be completely different.
Yeah, so we have to think of something completely different. The other way to answer the same question is that actually if you are allowed to make the circuit even more restrictive somehow, in a weird way, like set multilinear, okay, then recently in this CCC 2024, Mike Forbes proved this result that you can set multilinearize over all characteristics. And yeah, that's what is known. But that was an aside. If you didn't catch it, don't worry about it. Okay, but it's a very interesting open question whether this construction, so it appears in our paper, it's like half a page, very easy to understand. Can we make it work over all characteristics? It's not known. And it will actually have some implications to some other interesting problems. I mean, okay, interesting I take back, but some other problems. Yeah. So it's a very interesting question. We don't know how to do it. The only way we know how to make this work, we kind of have a bottleneck for that approach, but could be some other approach. Yeah.
Is there some reason why that exponential dependence might be tight? Like, do we expect maybe in some future we'll be able to get that lower? Or?
Yeah. So if you try to do it in the way that this works, then I think this is sort of indispensable, or some function like this is indispensable. But in general, I don't know. I don't see why it should be this. Yeah. Not sure actually. Yeah, I don't know any reason to believe that, yeah. For elementary symmetric polynomials, you have homogeneous circuits of size. Yeah, so I don't know. There is some exponential dependence that is like not truly exponential, it's like much lower for some polynomials. So yeah, it's possible. Okay, good. And now I'll just tell you a little bit about how this homogenization works. But, and it's a very simple idea, as I said, it's like half a page. So I just give you the flavor of the idea, and I'm presenting it also because we just talked about, just in the beginning of this discussion, we talked about something very, very similar. So let's try to understand how do I homogenize depth 3 formulas or circuits. Okay, so any depth 3 circuit looks like this, right? There's a sum of products of some affine forms. And if my field is large enough, I can just say this constant is a 1. Just divide everything, scale everything out. And maybe there's like a constant sitting outside, but I don't care. Okay? So a general depth 3 for circuit looks like this. And what are we interested in? We are really interested in computing a degree d component of this, right? Of this polynomial. In every summation, we just are interested in computing a degree d coefficient, like degree d part of this object. But the degree d part of it is nothing but elementary symmetric polynomial of degree. That's what it is. Yeah, because the degree d component just needs to take degree d many things from these LIs and ones from everywhere else. So it's just the elementary symmetric polynomial of degree d. And then, you know, these are called Newton identities. Newton identities express elementary symmetric polynomials in terms of slightly different power symmetric polynomials. Yeah. So what they do, so just look at this identity. I less than j, some ij, is nothing but summation xi the whole square minus each like single xi square and the whole thing divided by some constant, in this case 2. Yeah. And you can do the same for 3 as well. You can take summation xi the whole cube and some sort of inclusion exclusion kind of identity. This is called Nutan identity. Yeah? Nutan identity is nothing but expressing elementary symmetric polynomials in terms of power symmetric polynomials. Power symmetric polynomials are just this. Power symmetric polynomial of degree d is simply this.
Wait, isn't that I less than j?
Yeah, maybe. Yeah, I less than j, sorry. Yeah, that's the elementary. I just wanted to write elementary symmetric polynomial of degree 2. Sorry. Yeah. And these are called Nutan identities. This is like the whole expression, and basically the exponent. So this is what one does. Notice that these polynomials are super easy to compute. Yeah, it's just summation of some variables to the power something. So these have small formulas. Yeah.
What makes this not work in characteristic P?
Very good question. So this doesn't work because you see, notice that divided by 2 here, and for higher degrees it's like divided by d factorial here that comes up in these Nutan identities, and that makes it not work over small characteristics. So unfortunately. And if one could come up with Nutan identities over small characteristics, we would be done. But we show in a paper that actually that's not going to be possible unless something else happens. Something unbelievable happens. But you know, you don't need to use Nutan identities. Maybe you can use some other identities. So yeah. Okay. So this is all I wanted to say about this part. What about formula homogenization? So you could always start with a formula. What did I do here? Why did I say? Yeah, this is fine. So you know, just start with a formula, homogenize it. You'll just get a circuit instead. Yeah, because that formula homogenization we talked about just gives a circuit. Imagine delta is not the one, not constant, but arbitrary delta. Even then, the homogenization, the folklore result I told you about, which I sketched the proof of, blows up the depth by 2 only, even there. So you will get a circuit of this size. Then you can always go from circuit to formulas, you know, by just copying things a bunch of times. You could do all this. And if the depth is constant, this would be fine also. Yeah. What did I? Yeah, actually, let me say it more carefully. So delta is growing; it's very large. Then circuit to formula will just happen as is. Formula to circuit conversion in homogenization will work as is, and then you blow it up, and you get some formula of humongous size. Yeah, this is not very good because, okay, maybe, sorry, I'll come back to this slide in one bit, okay? Sorry about this, I wanted to, okay, let me just finish this point. So, okay, what I don't like about this slide right now is that the delta will make you think delta is a constant. Yeah, but I don't want you to think of delta as a constant for this slide. Yeah, I want you to think of delta like log s. Okay, so just with this caveat, the slide is good. Start with a circuit formula of size s and depth log s. You can always assume this without loss of generality, but I'll tell you about it next time. Start with a circuit of size s, depth log s, convert it into a homogeneous formula, but unfortunately it won't be a formula because we don't know how to do this within a formula. The depth will blow up, it will become 2 log s, let's say, but the size will be pretty tractable. Then I could convert it into a formula, and if the depth is log s, then you would get a formula, starting from a formula, a homogeneous formula of size poly s and d to the log s. Okay, d to the log s is not terrible actually. You know, it's like not really exponential. It's like d to the log s. It's fine. Yeah, and this you can do. So formula homogenization is possible up to this size. And in some recent and older results, slightly better is also known. So what this slide is trying to say, let's just read it out. If f of x has a homogeneous degree d polynomial, if f of x is a homogeneous degree d polynomial, and it's computed by a formula of size s, then you can homogenize it better if the degree is small. In fact, you just don't blow up at all if the degree is small. And if the degree is slightly large but not all the way, then you do get d to the little o log s. Okay. And why do I want to tell you such a technical statement? I mean, this whole series is supposed to be a bunch of facts that, you know, overview, bunch of results that you can take back, you know, concrete stuff. So yeah, I would like to zoom out of this slide a little bit. Don't worry so much about these numbers specifically. But what this is trying to say is kind of important. It's trying to say that if you were to prove general formula lower bounds, okay, so tomorrow you wake up and say that I want to prove algebraic formula lower bounds. This is my goal now. It's enough to prove lower bounds for homogeneous formulas that are, you know, and the lower bound can just be better than this. So you don't need to prove exponential lower bounds. You don't need to prove lower bounds for general formulas. So this is one example of how structure helps lower bounds. Right? We did some jugglery. We brought down the general formula into a homogeneous formula. We molded it as a homogeneous formula. We noticed that it does not incur the obvious blow up in some settings. So in some settings actually it saves on the obvious. It's better than the ad hoc method. And this allows us to say that, okay, now I don't need to worry about proving lower bounds in the most general case. Proving lower bounds for formulas that are homogeneous is enough, as long as I prove lower bounds slightly better than this function. So this theme will repeat itself a whole lot of times in this discussion. That you take the circuit, mold it into something nice, and now say that, okay, for this nice thing, maybe I'm able to prove a lower bound. So that's kind of what I wanted to say for this slide. Yeah?
Maybe you also want to add that you were able to actually prove lower bounds.
Yes. Yes.
By doing exactly this.
Yes, indeed. I think I say it somewhere, you're right.
Okay. And it's not just a conditional statement.
Yeah. Sorry, yeah. I should have said that. You are absolutely. So in fact, this methodology has helped. It's a very fruitful thing because recently we were able to prove a lower bound, which I'll talk about in the next lecture. And this went exactly like this, that we were able to mold it into more and more special kind of circuits. And now for that special circuit, we were able to prove a lower bound. Okay, so it also works sometimes. But it's, in general, I think both kind of results are interesting. And also, like, philosophically, it's very much like what Ryan has been doing in Boolean setting, right? Like, it's very different, of course, but also, sorry. Sorry to embarrass you like this, but, you know, like, algorithms imply lower. Like, you get better than brute force algorithm for SAT, then you get lower bounds for, you know, ACC versus NX. So, this sort of stuff. So, it's like, at a philosophical level, it's the same. Of course, in the details, it's very different. But, yeah, good. Okay. Yet another kind of structure, set multilinear. So I didn't even define what set multilinear is. I'm directly giving you a theorem, but you already know what set multilinear is. It's what iterated matrix multiplication is. Okay. So let me define it. A polynomial is said to be set multilinear if there is an underlying set of variables like x1, x2, xd that we had right in the IMM setting. And the polynomial has the property that every monomial in it uses exactly one variable per matrix or per set of variables. And then a circuit is set multilinear if every gate inside it computes a set multilinear polynomial. Would you like me to write this down? Is set multilinear if each polynomial in P has exactly one variable for set. That's it. So iterated matrix multiplication is an example of such a polynomial. Now, determinant is actually an example of this. If you consider the partition of variables as row partition or column partition.
Every xi is, I mean, the subscript has two.
Doesn't have to have.
Yeah,
Doesn't have
this
to
is
have.
because usually we're looking at like.
Yeah.
set, like
For IMM, yeah. It's fine. So what does this statement on the slide say now? It just says that you can also set multilinearize. Just like you could homogenize efficiently, you can also set multilinearize efficiently. Yeah. This, interestingly, due to Forbes' result now, works over all characteristics. So it uses something called as a Binet-Mink identity. It's like we use Newton identities in the other one. Here they use Binet-Mink identity. And that doesn't have these constants hanging around. So it works over all characteristics. Yes?
Is it easy to write? What is the Binet-Mink identity?
I would encourage you to just look it up online.
Okay.
It is a bit of a mess, but
okay,
yeah.
Sure.
It's kind of like taking some subdeterminants or right.
Oh yeah.
Yeah. Okay. So that's about set multilinearization and homogenization. I'll tell you one last thing, maybe, or maybe two things I'll tell you. Here is an interesting one. Okay. Here, this is also a structure result. It says that if you were able to compute a polynomial in size S, say circuits, then you can also compute simultaneously all first order derivatives in about the same size, order S. Okay, what are the first order partial derivatives? I mean, this is something I expect all of you know. Let me know if I need to define this. But the interesting thing is you're computing all of them simultaneously. Yeah? So that's the interesting thing. The typical blow up would be n times s. Yeah, because you'll compute the first partial derivative, the second partial derivative. So you can always do it in n times s size. But this is saying you don't need that extra n. Okay? And the proof is by some clever induction. Again, I'm not planning to do the proof here. What's interesting is we don't know how to do it for second order derivatives. In fact, in the problem sheet, I have a little problem for you. If you were able to do this efficiently, second order partial derivative, you would improve matrix multiplication exponent. It's a very simple reduction. It's in the problem sheet. So think about it. Yeah, but if you were able to compute second order derivatives, then you will in fact be able to improve the coefficient for the exponent for the matrix multiplication. So this is a very interesting open question.
But that's n square many second order derivatives, right?
That's right.
So the algorithm should be like S plus n squared?
S plus n squared, exactly, yeah. Because you have to output n square things, so yes, exactly, S plus n squared.
Also, it's just back propagation?
Yeah.
Like for machine learning?
Exactly, yeah. So, very good question. So, the question was, this first order derivatives, does it have anything to do? So, when you do, when we have these neural networks, right? How does the neural network algorithm work? You do this gradient descent a bunch of times and then you do back propagation. Back propagation is nothing but computing first order derivatives a bunch of times. And the fact that it can be done efficiently comes from this, really. Comes from this construction, yeah. Yeah, so the back propagation algorithms basically just simultaneously compute first order derivatives of all these edges simultaneously, right? So, and the fact that it can be done efficiently, I don't know how practically it's being implemented, but what I hear from people is actually it is being, like, it's a very similar thing is being used there. The fact that it has exactly about the same size, that's important for them.
Do people in Algebraic Complexity use this for funding applications?
No, I don't think. But I mean, now, you know, it's good for us that somebody is using it. Yeah. All right. So I'm coming close to my time. But the final thing I'll tell you about today is this depth reduction result. And I have a proof sketch in my slides, but maybe I don't have time for this. So let's see how this goes. I have like 3 minutes. And I want to tell you the proof of this. So what is it saying, firstly? It's trying to say that if you have a polynomial, f, being computed by a formula of size s, then it can also be computed by another formula of depth log s and size poly s. That's all. Yeah? So depth reduction is just this statement, that you can bring down the depth to log s. Okay? And again, I have proof mostly by pictures. The main idea behind this is, though, that you're looking at this tree. It would be nice, very nice, if you can find like a midpoint of this tree and divide and conquer. Yeah? That's really basically the idea. So let's look at the picture. I have this tree. We know by this, whatever it's called, tree lemma, or what is it called? It's called something, right? That every tree has a vertex in it, has a unique kind of vertex actually, that divides the tree into almost a fraction, like almost the same fraction, say 2s by 3. You've seen this fact before? Very easy to prove. Just go down the heavier child and you'll find this node with this property.
Need not be unique, right? I mean, if it's already balanced, then.
Yeah, you're right. Yeah. Good luck. Good catch. Yeah. There is a node. I just care about there being such a node. Okay? And then now I just break this into 2 circuits. This shaded one, I mean rather the drawn one and the shaded one. The colored one and the shaded one. And I try to, of course, each of this has small size. So recursively I could say compute it. How do I combine them together? So the thing to notice is that if the polynomial computed by this, I denote by this weird thing, polynomial between v and u, let's say, polynomial at u, then the polynomial at v is nothing but polynomial between v and u with this new variable, but the variable substituted with polynomial at u. I've done nothing, it's just rewriting. But now the interesting thing to note is that this polynomial is actually linear in this y variable, because it's a formula. Any node can be used at most once above it. So it's a linear polynomial, somewhat like this. And so, you know, this linear polynomial, which looks like ax, y plus b, you can just compute what this ax and b are, a and b are. Because when you substitute y equal to 1, you get one equation. Substitute y equal to 0, you get another equation. You subtract them, you get something as a value of b. And then you also get something for a by back substituting. Yeah, so it's not only a linear polynomial in Y, these components that sit around Y are easy to compute. Okay? Which means the overall polynomial f of v, this has to be an equality sign, I don't know why the equality went away. This is nothing but ax, y substituted with the correct fu, and p. So it's essentially like we have expressed the original polynomial as some 4 copies of smaller polynomials, and then the recursion just sets in, right? So the size recursion is just depth s is depth 2s by 3 plus order 1, and size is some 4 times size of smaller things plus order 1, which is 4. Very simple, very interesting, and good to know. So I kind of went over time, but yeah, thanks. That's all I wanted to say.